Which is that?
Okay, thank you. So now this is theorem 2. And in this case, we're going to give the reference crease and the deformed crease, and they're going to be related isometrically. So you call it an inextensible curve. So you give an inextensible curve, and then you put it in free space, and you want now to give the surfaces, find the surfaces on both sides and the rulings. This is actually a lot more tricky, but it can be done. And it's a lot more tricky because of this, is that you could take the deformed configuration and you can draw any old bad curve on that deformed configuration. And then you could take the inverse image of the curve back to the reference domain, and you would get a possible crease, but the regularity could be horrible. And so so you have to be very careful about deformed, assigning just the creases. Okay, so we have a crease in the reference domain, it's flat. We have a crease in the deformed domain, isometrically related, and we want to now have two sides to it. And so what makes it smooth is, what makes the curve smooth is there are two smooth surfaces meeting the crease. So that has to be somehow built into the okay. Another issue is if you're not careful, you can take two pieces of circles and you can join them by a line. You can somehow, first of all, rotate one and join by a line. So that would line, the curvature would be 0. And if you you can show that you can't put, in that case, you're not able to find isometric surfaces, isometrically mapped surfaces which meet at that case. So there's all kinds of difficulties with inflection points or with flat regions. So somehow, and special things you have to do with, say, the third derivative vanishes. And if the third derivative doesn't vanish, and you have to look at higher derivatives, it's quite, if you really want a general theorem, I don't know how to do it, but what seems to make, so I want a theorem that's you can use actually. So we assume the creases are real analytic. That gets rid of a lot of possibility, a lot of crazy things. So for example, if you have a flat region, the whole thing is flat, and so forth and so on. So then we can write a theorem. Here's theorem 2. So let's go slowly because I think I went too fast on the last one. So I'm going to take two creases. They're going to be real analytic on some domain, and I'm suppose the creases, isometric mappings shorten distances. Shorten distances, so the creases have to shorten distances. So so this is a shortening condition on the creases. And we suppose there's no inflection points except at a finite number of points. So these are quite strong assumptions, but I mean, still gives us a lot of things to use. I mean, the most important thing are these formulas because we use them repeatedly. And we assume the first non-zero derivatives occur at level ki, and that occur at a finite number of points t1 to tn. And then there's some definitions. And then in that case, you can write a formula for the normals to the deformed crease. This delta plays an important role. There's also some plus or minuses that come up. You can define the tangents to the rulings in the deformed configuration. You can define the tangents to the rulings. So this is the tangent to the ruling deformed configuration, this is perpendicular to it. This is the tangent to the ruling, and the reference domain, this is perpendicular to it. It's said, and this is just repeated. Then you define the rulings by these two formulas, just like in the previous theorem, and let y hat be the induced mapping between rulings, and then you prove that this y hat is isometric. Okay. So, and it's a really messy calculation, so I'm not going to. But the great thing about it is we get explicit formulas that we're going to be using all the time. So there's formulas. So this is can be illustrated nicely. Yeah.
I get a bit lost in what was prescribed here and what you would choose.
The main thing that's prescribed is the reference crease and the deformed crease. Nothing about rulings.
And the rulings you choose.
No, nothing about rulings. The rulings are given, are then the conclusion of the theory.
Okay.
They're
So basically, if you have the reference crease and the deformed crease, then you have to choose the ruling in a certain way to be able to construct the.
Well, you get formulas. See, here's the normal to the two rulings. Sigma is
They depend really on.
there's actual formulas in terms of the two curves. It's not easy to get that formula, I can tell you. And there's formulas for the.
But the statement is that you can always do it, no matter, I mean, the curve shortening is this.
Yeah, that's.
Any reference curve or any deformed crease.
Yeah, I mean, but there's a lot of strong assumptions here. In real analytic curves, there's a finite number of points, where, so we don't have, accumulation points and things like that. So there's strong assumptions of smoothness.
And uniquely, that's what we want. Because then you say there is.
Yeah, there's a delta, there's a sigma here that gets to be chosen. Yeah, so it's more or less unique. Yeah. There's a formula you can, and there's a proof. I mean, I can give you. I can see. I need to give you the proof.
You also mentioned that there was sort of transversality conditions, and that's somehow implicit here because you have to somehow infer that there's transversality
Right.
afterwards.
Yeah, that's right. So this formula is not parallel. This formula would not be parallel to y0 prime. Right.
So basically, ignoring problem with degeneracy, then the main assumption is just that the curve got shortened.
Yeah, the main assumption is the curve is shortened and there's not limit, there's not accumulation points of, so there's a lot of smoothness.
Yeah. So let's ignore issue of degeneracy.
Yeah.
Okay.
And the pictures, because of the plus or minus sign, you get 4 pictures. 2 of them are degenerate. You can see that this is the same as this. So this, this picture is this picture here combined with this picture there. And so that's the results of, that's a picture of the results of the theorem. It's just plotted using the formulas that I just showed you. And now we can understand immediately how to do Frank-Gehry buildings. Because I'm giving just the reference crease and the deformed crease. So now I give the deformed crease, but I give 2 reference creases. 2 different reference creases. And I make sure they're curve shortening in both cases. So I give these 2 reference creases, and I give this deformed crease. And then I just apply the theorem to this reference crease and this deformed crease. And I apply the theorem to this reference crease and the same deformed crease. And this is what I get. So you just have to, so that's in a sense how Frank-Gehry, I believe, how Frank-Gehry buildings are actually built. I don't know if they're designed. I don't know if these guys found using theorems, but whatever method they have. And there would be 4 cases using those. Part is curve, it has to be curve shortening. So in this case, you use the theorem to get this side, and of course there's another side, you throw the other side away. Use the theorem to get this side, and then you throw the other side away. And you're left with that. Yeah. Okay, now, so in this theorem, just to avoid all kinds of nonsense, we're going to avoid the inflection points. So the second derivative is not zero along the whole curve. And so this is when we're going to give the two normals to the two surfaces. So this is a little easier to state. Give the two unit normal depending on the parameter S. Define the rulings by these two formulas. There's the formula for the deformed crease, and I'll come back to this. These formulas right here, and then there's two formulas, one with +1 and -1 for the reference crease. Again, they're just formulas in terms of the given information. There's the rulings for the reference crease, and there's the reference rulings written out. Then you take the induced. It's always the same like that. You take the induced mapping between rulings, and you prove it's isometric. And then there's the reason it's written this way is that this gives two curves for the reference. Rulings, or two formulas for the reference rulings, and the condition that they agree at the crease is this condition. Sometimes, for example, that Frank Gehry case, we wanted to have two different cases. So basically, in this case, we give the two normals and we get everything else. Okay, and I don't have, even though this picture has inflection points like there. The theorem, at least the statement of the theorem, doesn't include that. Okay. Reference creases, reference. Okay, so I'm going to describe a method. This is a quite nice method. Lots of fun for making. It's a kind. You could call it lazy man's method of doing it. It's this group orbit method. And it allows you to do some very simple calculations and get very complex origami structures, many of them. So it's based on isometry groups. So those are the groups that are come up in crystallography. So those, if you would, the repository for those groups is the International Tables of Crystallography. And it consists of elements. Sometimes they're written this way. I'll use this notation. The Q is an orthogonal matrix and C is a vector in R3. So I'll always be in R3. And an isometry can act on points in R3 according to this rule. And if you have two isometries, the way you multiply them is this way. So that's the multiplication rule for isometries. It might look a little bit strange, but it won't look strange when you realize that this is the rule for acting on R3, just QX plus C. And so where does this come from? It comes from the product of two isometries acting on X is using this statement is G1 of G2 of X. So it corresponds, the group product in isometries corresponds to composition of mappings. And the identity is identity 0 and so forth. So in a way, this action on R3 creates a topology for the groups. It's actually topological groups, and we'll use that aspect. So, and we're going to use abelian groups mostly in the examples. But so in abelian groups, use generators and relations. The generators are some isometries. The relations are that they commute with each other. But you could use more general generators and relations and similar ideas. Although I'm not going to use, I'm going to use it, I think, exclusively abelian groups. Okay, so that's the way. So the simplest example illustrated by piecewise. So I'll take you through the steps of how you use this group orbit method. So we'll go back to the Mura-Ori tile that we already analyzed, and I'm going to make it a parallelogram defined by x1, x2, x3, x4. And I'll take a point x0 inside this parallelogram such that sum of opposite angles equals pi. So all those results we had in the first lecture hold. And let's see, and okay, it's not that yet. So then there's also these two red curves. These two red curves are obtained by trigonometry. It's the law of cosines. And they're the locus of points where I can put x0 and the sum of opposite angles will be pi. Okay, so it's just put x0 on one of these red curves, draw these lines to the four corners. You get something that can be folded. We already figured out how to fold it. Even those are the formulas. If I fix one of the regions, this is a continuous function. As long as this agrees with this at the appropriate crease, and we found that it's in fact T1, and we found that that's this condition. It's equivalent to the angle eta being plus or minus omega. So again, there's one free parameter omega, and there's the choice of plus or minus. That's the beautiful. And this is the formula for the homotopy. Let omega go from 0 to pi. So for example, if you take plus omega and you partly use this formula, you can take omega as the free parameter. So you choose omega to be something, and you can plot with Mathematica the two examples with plus omega and minus omega. And so that's the intermediate state. If I kept going with omega, this would eventually be flat. Okay, so that's what I did in this. Okay. Now, yeah, just so you know, because if you're familiar with Mura foldings, the classic Mura foldings, that would be the case of a rhombus, and rhombus. You notice this doesn't look right, but these two curves degenerate into lines. These two lines in the case of a rhombus, and then x0 can lie on those two lines, and you can see sum of opposite angles is pi just by looking at it. Okay, that's called Kawasaki's condition. So we're going to have an isometry group for the reference domain. We're going to have an isometry group for the folded structure, or partly folded structure. So that's why I chose the parallelogram, because I can use a translation group. So this is the way you would write the generators of the translation group, and powers of those translations corresponds to adding integer times t1 plus integer times t2, according I times t1 plus I times t2. So that's a abelian group. If I take a single tile and I operate that group on the points in a single tile, I get a periodic array of tiles. I guess everybody knows this, but that's and now I'm going to take two generators that commute. Okay, as I said before. So I'm going to allow, an orthogonal matrix here. Actually, I'm going to assume it's an SO3 here. This one's also going to be, oh, it's right there. It's going to be an SO3. And there's a little technical thing. I'm going to assume, 180-degree rotations are symmetric, and that leads to some kind of different origami structures. It's still, you can do many things, but it's a special case, and it's not the generic case. And but you can do it if you want. I just don't want to do all the cases. So I'm going to assume that R1 and R2 are not symmetric, which in fact means that they're not the identity or not 180 degree rotations. So there's no problem with doing that case. It leads to some very different looking origami structures, but I just don't want to do it. Not so interesting. If the two, think of that product rule, if they're not symmetric, and they commute, so the product rule is here. It's just, it's this rule. So if the two generators commute, then the rotations commute as well. And in the case that the R1 and R2 are not symmetric, this means that they have a common axis. So R1E is R2E equals E, okay? So we have two, that's a necessary condition that they compute. Together with the fact that they're not symmetric. And then if they commute, they have the same axis as I just say. So the only free parameter then is the angle. So I'll use that as a subscript. So R1 E equals E equals E, and the angle in R1 is theta 1, and the angle in R2 is theta 2. Now, so I'm just trying to figure out when these two isometries commute. So a necessary condition is that, at least in that case. And then we have the C1 and the C2. So there are going to be restrictions on C1 and C2 coming from the fact that they commute. And so I can always write C1. C1 is any old vector in R3. I can always, so far anyway, I can always write it as something along the axis plus something perpendicular to the axis. And although R theta 1 has axis E, identity minus R theta 1 is invertible on the axis perpendicular to E. So in that case, it's always possible to find a vector perpendicular to E so that C1 can be written this way. And so there's a Z1 and Z2, which are perpendicular to E, and I can write C1 and C2 that way. And the reason I do that is that, you know, is that okay, I just stated anyway, it's very simple linear algebra, is that a necessary and sufficient condition that they commute is that this Z1 equals the Z2. So there's the general form of two isometries that commute such that the R's are in SO3 and they are not symmetric. Okay, question? And the conditions are that Z is perpendicular to E, and E is a unit vector, and so forth. And there's this tau 1 and tau 2. So we're going to do that, and then we're sure that they can be. We'll talk more about this later, but we didn't say anything about helices, but in the end, these are so-called resultants, they're helical isometries. So they describe, if I apply G, I can apply G to points in R3. If I apply G to X, I get this point, G squared to X, and so forth, and I create equispaced points on a helix. So they're helical transformations. And the tau represents the pitch, so would be the vertical distance between this point and this point. In this case, it's 7 tau because it's 7 points. And E is the axis of the helix, and Z is the point along the axis. So the origin could be somewhere else. So you can move it around. It'll be useful. Okay, and theta is the angle between projected G of X and X. You project down. Okay, now we do the following. So this is how it works. Is we know how to make a partly folded Origami structure, which came from a parallelogram. So this came from a parallelogram. So we're going to take this partly folded structure. And now G1 and G2, they're isometries. They preserve distance. We're gonna, and you know, even though this is partly folded, this length equals this length because because of course this is piecewise isometries, and it started out as a parallelogram. So that therefore this was maybe the bottom of the parallelogram. This is the top of the parallelogram in the undeformed configuration, but now it's partly folded. Anyway, I think you'll believe me when this length equals this length there. And so there's an isometry. There's probably lots of isometries that take this line into this line. So I'm going to arrange the parameters. So I have quite a few parameters in G1 and G2. Oh, I have the tau, I have the theta, I even have the axis, I have the z. So I'm going to arrange those parameters such that G2 maps this edge into this. And I'm going to take the parameters in G1 so that it maps this edge into this edge. Of course, there's going to be some free parameters left over because I had a lot of parameters. And I'm only requiring that it maps this edge into this edge. I could also consider, it can do anything as far as rotating about that edge, either before or after, and so forth and so on. There's a lot of choices. Unfortunately, I have the movies. Anyway, so now I'm gonna. So now this is just a schematic view of this. I wanted to draw it separate. And so this G1 maps this edge into this edge, and G2 maps this edge into this edge. But now I take G1 and I apply it, instead of applying it just to this edge, I apply it to the whole partly folded structure. And it's an isometry, so it gives me another copy of the structure. And of course, they agree there because I did that. And I take G2 and I take it on this structure, and it maps this into this, but I apply it to the whole structure and it gives me this into that. And then the beauty of commuting of abelian isometry groups is now I take the product of G1, G2. I apply it to the original structure, and it fits perfectly along here. And I take G1 squared times G2 or G1 cubed. I take the whole orbit of the group on this structure, and it builds me a beautiful orbit. And you have to, now you have the hard job of lots of algebra, taking care of the parameters. There were two parameters for the angles and the R's. There were, I'm sorry that the notation has changed a little bit. There were parameters in the C's, and then there was the E, the axis of the R's, and there was this point. So those all become useful parameters in doing this calculation. And there was also the choice of plus or minus. That was also in the original calculation of the very uniformity. And in the end, you still have two free parameters, the omega, and there's a second free angle, which I'm not going to try to describe. So it's just algebra.
So where's the dependence on this point on the loci? There was this red line of locus.
Yeah, that's only there. You fix that point. And that's only there to make sure it can be folded, folded. And there's a homotopy and so forth.
Did you include that parameter here as a degree of freedom issue?
No, I didn't, because usually you think of the reference tile as given. This was piecewise linear origami. You don't think that you could
think of flexibility, the extent to which.
Yeah, I mean, then you would be talking about different, then you'd have to change the creases as well. Usually people think of a tile as a, at least with piecewise linear origami, as a rigid. So you can't change the crease. You can't move the crease but you could, in some soft matter origami thing, you could think of doing it. That's one of many directions. So G is a group. So this builds you a structure. So what kind of structure does it build you? So ideally, you take these free parameters in G1 and G2 and you start varying them. And you could vary them continuously from the unfolded structure to the folded structure. And ideally, this would happen. The tiles would begin to deform, and this thing would begin to maybe roll up. And as you continue to deform the tiles, it would roll up, and it would perfectly match and form this cylinder, with a bumpy cylinder with the tiles on the side. So that's what you would like to happen, but that won't happen. But it turns out that it can happen under something very simple, something very well known. So one thing that could happen, you could end up with a mess of, when you start changing these parameters. What am I changing? I'm changing just omega here. So that was the omega in the original slide on mirror folding. So that was this partly, I'm supposed to stand a little bit more to the center. So yeah, so that was the slide on the original mirror folding. So that has to do with the unit cell, how it gets folded as you go one to the other. So this is as it's changing. And then everything else is slave to that parameter. Now, alternatively, you might not get this, you might get just some, it still will have a nice beginning, but when it all comes together, you might get some mess of intersecting tiles. But that's actually related to something very well known. In fact, it's an abelian group, so there's no problem about that, but it might not be a discrete group. Okay? So discreteness of the group is very much related to whether this comes together perfectly to form a perfect helical, structure. Well, if you're teaching about discrete groups, it's such a concrete example. It's a nice thing to know about. So what is a discrete group? You take any point in, let's be in R3, so take any point in R3, and the group can act on points in R3. So you take the group acting on that point and you get points in R3. They might have accumulation points. If for every point in R3, you take it there, its orbit, if there are no accumulation points, then it's a discrete group. Okay. Well, there's also more general definition, but that's a good definition for us. So what are the restrictions on these parameters so that the group is discrete? That's what we need to know. Yeah. So a helical group is by definition a discrete group of isometries. So this is something maybe you would it's should be in the international tables of crystallography. It's not there because the helical groups are not there. They're not there because of an accident in classifying these groups. But anyway, so what is a helical group? It's a discrete. So that's a definition. It's a discrete group of isometries. And I described what discreteness was. That does not contain. First of all, it does not fix a point. So, and that means isometries can act on points in R3. So it doesn't fix a point, and it doesn't contain any pure translations. Pure translation was identity bar C. It doesn't contain any of those. Those would be isometry groups with just pure that fix a point. That all fix a point would be the point groups. But we're not going to fix a point, and we're not going to allow any pure translations. So we're going to create a group. Those are the helical groups. What's that? That's an assumption. No. This is. Yeah. Sorry about that. Good point. Yeah. Thank you. Yeah. So these don't have to be. In fact, I'll show you what they are, so you'll see that some of them are not the other. So there's an interesting. Yes, right,
So
right.
they're all rotating along one axis,
Right.
which is called E.
Right.
Yes,
Right.
not this again.
Right. This is a bit more general. And actually, the next thing I'll tell you will really clarify that question. These groups are not in the international tables, even though there's supposed to be a volume E, which includes groups which do not have the full set of 3 linearly independent translations, but it's not there. It's a kind of accident. It's kind of interesting story. Maybe I won't tell that story in the interest of time, but anyway, so because of that, we worked out what are the helical groups. So you take this definition, it's all there, and you use the properties of isometries, and you work out what are all the helical groups. So I'm happy to share it with anybody. It's like about a 25-page calculation with lots of cases, and I think somebody else must have done it. So I didn't publish it, but I'll be happy to share it with anybody who needs to know those groups. Anyway, this is the answer. These are all the helical groups. So the notation is here. This is similar to the things we're looking at. This is a screw transformation. In fact, it's exactly what we're looking at. So it's QE is E, and so forth. You see is exactly what we've been describing. G is something without it's a pure rotation. And so it's just a pure rotation with angle 2 pi over an integer. And F is 180-degree rotation with axis perpendicular to E. And then all the helical groups can fall into one of these categories. One is just powers of the screw transformation. Another is its powers of the screw transformation with this thing whose 180-degree rotation. And this one, all the elements commute. So this is the one, in fact, we're going to use. So this is a helical group. And this one, so the elements of this do not commute. The elements of this one do not commute. And this is a subgroup of this. So this is the more general case. So we'll be using this case. Okay. Actually, you may know graphene. Graphene made from carbon. There's lots of different graphene. Not graphene. You may know carbon nanotubes. There's many different carbon nanotubes. They all fall in this category. And actually, the F is the thing. If you know carbon nanotubes, there's this pair of carbon atoms that gets mapped around. The F relates one in the pair to the other. So you realize how special carbon nanotubes are when you see that there's only these 4 helical groups. Okay, so that's something we can use, and we'll use this. And these elements commute. So if I take 2 of these, H to the N1, G to the N1, and multiply by another one, I get back in this group. And this has the physical interpretation. H is a screw transformation, so like this. And the G is a pure rotation with the same axis. Right? Oh, that's and then if you want to illustrate those 4 groups, you can take a single ball and you can apply the group to a single ball. And in the case of that group 1, we apply it to this ball down here. We get a picture that looks like this. In the case of group 2, we get a picture like this. And this element F takes the red into the blue, it's mapped around by the other elements. So this is like a carbon nanotube, but the lattice parameters are very different from the carbon nanotube. And the group we're going to choose is this one. So I colored these elements by the value of n or the value of s. Those are finite. So this is with the value of n. This is the most general case, the case 4. So we're going to choose this case because that's those commute, and we've solved the problem of being discrete group, and so And now, we want to, yeah, so we're gonna choose this to correspond to our previous, they're commuting, and we're gonna assume that the tau is not equal to 0, because the tau, that was with the previous notation, so there's the tau, so these taus are not 0. And in fact, you can, under some condition, only tau is not equal to 0. You can, instead of using these generators right here, H and G, and we have a finite list of powers, you can use so-called nearest neighbor generators. So that's G1 and G2 that take you to nearest neighbors. That's obviously can be very useful. So that's what we're going to do. So we use nearest neighbor generators. And then the theorem is that when you have nearest neighbor generators, it makes tau1 an integer times tau, and tau2 another integer. So again, something it's not so important, but anyway, that's the way it is. And then there's some restrictions. Then this is a discrete group, if and only if these powers satisfy this restriction. I'm sorry, if and only if there exist integers p star and q star, such that this m1, this m2, this theta1, and this theta2 satisfy this. So maybe it's too much algebra, but there's conditions you can set, using these nearest neighbor generators, in which are under some mild conditions are necessary and sufficient that this forms a discrete group. Okay. And these are the conditions you have to satisfy. So let me describe it physically. Physically, you have this. We were rolling this up, and then we were rolling this up and having it meet. That's how I was suggesting we would make this cylinder from the mirror folding things. And we're rolling up by changing parameters. And so what does it correspond to P star and Q star is you could roll it up like this, or you could roll it up like this. So there's many ways to roll it up. And this tells you this tells you the ways you can roll it up and get perfect matching. So the end result is you'll always get a picture which looks like this if you satisfy the results of this theorem. What's that? This is commutative because, it is because we chose that group, and that group consists of these elements. We chose different generators, but the commuting property still holds. Yeah.
Actually, I'm slightly confused with that. Do you mean that that's the free group generated by these, or if you write it like this and it looks like commutative for all the groups already now?
Yeah. So you could also. It's the free group generated by those as well, because G to the power 9 is, well, the angle of G is 2 pi over I. So,
I mean the other group.
and they commute. Oh, the other ones.
Because otherwise you would have something like H, G, G, H, they would be all different.
Yeah, so, H doesn't commute. Okay, so that's a good question. H doesn't commute with F. No, H does not commute with F, but it commutes with an inverse. So H times F, well, I don't remember. H times F either equals, H times F equals F times H inverse.
Okay, so there's a relation.
Yeah. So it would also be the free group generated by them in all cases, all 4 cases. Okay, so so there's a physical interpretation as you roll, and this freedom you just slide it along the interface. And then you get, so then you can make lots of structures, just using this procedure. make sure the group satisfies discreteness, and automatically the thing will close perfectly. You won't have a seam, and you can have a lot of fun making this. And you can also see, you know, there was this P star and Q star. They were parameters you could choose, and you'll get different with the same unit cell, you would get different choices as you change this P star and Q star. So what are P star and Q star? That's if and only if there exist integers. So you start playing around with these integers, and you'll get you know, different kinds of structures, which look like this, and you can draw diagrams with the free parameters. These were the two free parameters we had for the unit cell. And there's as I said, well, there's a way to think of this in terms of dislocations. Maybe I won't try to describe it. It's too complicated also for me to think about it at this point. But, okay, so we're lecture 3, but it's not time yet. So maybe what did I? Oh yeah, I'll tell a little bit more about this because it is maybe lecture 4 will be a little bit shorter. So what happens if you use a non-discrete group? I said you get a mess of things, but it's fun to look at what you actually get. So if you we're going to take 2 commuting generators, so 2 helical commuting generators, so the simple case, the original case, and but we're not going to satisfy that they're discrete, gives a discrete group. So what do you get? Maybe it's interesting, right? Especially for material planets. And this is what you get. You get, you know, as you take more and more elements and you start multiplying them out more, take the powers higher and higher, thing starts overlapping itself. But it kind of overlaps itself in interesting ways. So you have, you know, here you have a kind of monatomic lattice or helical lattice, and here you have a kind of diatomic one. So there's, nevertheless, even though the group is not discrete, there's still kind of interesting stuff here. And particularly gets interesting if you allow yourself to cut off the powers of the generators. So you take this non-discrete group, and when things are about to get messy, you just say, I'm going to cut the generators here. And that's a case that's right here, and you create in that case, you create a seam. And of course, it can be quite a bad looking seam, but then you can also play a little bit with the group parameters, and you can get a nice looking seam, periodic seam here. So that's quite interesting. And in fact, there are biological structures. There's microtubules actually have this structure. They have a seam, and it's possible that has biological significance because they're always coming apart and going back together, and it could be that this seam is a nucleation site for that.
So doesn't it mean that this development is correspond to a subgroup of your non-discrete group above?
It's not even a subgroup. It's just you write out the full group, and then you just throw away. So the group was G1 to the I, G2 to the J. You just restrict I and J to a finite set of R2. Yeah. In a clever way. I mean, you're doing it, you're cutting off the powers in a clever way. Actually, there's a person, her name is Ryden Tvarek. She's at University of York, is that right? Yeah. She has a method where she works on viruses, and she has a method for discovering the structure, some fine details of the structure of the surface of a virus, in which she doesn't describe it anything like this way, but she agrees that it's the same as this way. Her work is very interesting. That her work is equivalent to doing exactly what I've just described. She has some generators, or you can find some generators from her calculations, and you can just cut the powers in a very clever way, and you can get some interesting structures that she studies. So Now, so so that's a seam, so you can get a seam like this if I cut the powers off. I can also get a helical seam, and I can also get some different kind of helical seams. There's all kinds of interesting structures here that are not given by discrete groups that one should also study and understand a little bit better. So maybe this is a good place to stop. So originally, I'll just do it at the end of this slide. So originally I thought, you know what, in my usual life, I study phase transformations. And I thought, on these helical study structures, maybe we can have phase transformations. So we can have a blue helical structure. And we can have generated by a group, and I just leave out, I just take the power, so I just get the space in between. Then I'm gonna fill it with another helical structure. And maybe I can move this interface to convert the blue structure to the red structure. Unfortunately, it doesn't work. It's rigid. If you try to you know, you would manipulate the powers of these the generators so that to move this red interface one layer, keep moving this one layer. What happens is it also slips along parallel to the interface. So you could say dislocations, you get lots of them. And so as the red increases its area fraction, there's slip along the interface. And that would be not so nice, you know. So I mentioned this to my two postdocs, Fan Feng and Paul Plucinsky, and you know, so how do we have a phase transformation on a helical structure? And they came up with this example. I think it's absolutely fabulous. Is this? They said, well, you can take one of the phases and you can twin it. You can reflect it. You can do minus the identity. You can do it, which would be still considered the same phase. So I have to show it again. And that will take so the red and the blue are really the same phase. They're twin. And then you can do it without slip. So you have little extra freedom if you have this twin. So if you're familiar with bulk phase transformations, we also have twinning, and we also use the freedom of twinning to help make the phases compatible. It's somehow completely analogous here, but it's by a totally different method. The twins, I mean, the twins are not kind of, you know, it's sort of parallel. I mean, it's different in a way, but it's a wonderful example. I have no idea whether any real helical structure does this, but it's an interesting thing to think about. So I guess I should stop there. And,